Hi friends, welcome back to a new session. In this session, we'll discuss in chapter number 3, Synchronous Machine, starting methods of synchronous motor topic we'll see. Before watching this session video, please try to watch simple loop diagram of synchronous motor. So I already explained a simple loop diagram of synchronous motor. There I concluded synchronous motor is not a self-starting motor. So can you please try to recollect that, what I told, why synchronous motor is not a self-starting motor? See, to be frank, for having unidirectional torque in a motor, current entering into the armature winding should be AC. In synchronous motor, we are giving AC supply to the stator windings, nothing but armature windings, which are placed on the stator. So obviously, in armature winding, current entering is nothing but AC only. Though current entering in the armature winding is AC, instead of unidirectional torque, we will get bidirectional torque. So thereby average torque becomes 0. That's why synchronous motor is not a self-starting motor, I told. So reason I told very simple, because of inertia. The synchronous motor rotor will be having some inertia. Because of that inertia, the rotor of synchronous motor cannot able to respond for the fast and continuous reversal of armature current. That means what? Though armature current is AC, because of inertia, the rotor of synchronous motor treat those currents as DC. So synchronous motor point of view, DC supply is entering into the armature winding. Because of that, bidirectional torque is produced. So average torque becomes 0. Therefore, synchronous motor is not a self-starting motor. If you want, so obviously you have to overcome the inertia of that synchronous motor. So for overcoming the inertia of your synchronous motor, we are having some starting methods. Nothing but auxiliary motor starting, induction motor starting, or damper winding starting, and a synchronous induction motor starting. Okay. So please try to see that simple loop diagram of synchronous motor. There I told you why synchronous motor is not a self-starting motor. How you need, instead of unidirectional torque, why you are getting bidirectional torque, all those things we explained in simple loop diagram of synchronous motor. Please try to watch that video, and after that, just let us see in this session, let me explain some points regarding synchronous motor. See, generally in a motor family, I told you induction motor is very famous. In 90% applications, we are using induction motors, okay? And see, at the same time, synchronous motor is also having its own importance. Suppose synchronous motor generally it is preferable for low speed, large power applications. Low speed, large power applications. Okay. So why means at these applications, for these applications, I can say that synchronous motor is very cheaper than equivalent rating of induction motor. So if you see induction motor generally we are using, okay, but in this application, nothing but low speed, large power applications. So synchronous motor is very cheaper than equivalent rating of induction motor. That's the reason why we are using synchronous motor in low speed, large power applications. Okay, and see, generally synchronous motors are classified in two types. Salient pole synchronous motor and cylindrical pole synchronous motor. But most of the synchronous motors are salient pole type. We already discussed it. Salient pole machine means it's a low speed machine. Cylindrical machine means it's a high speed machine. So just try to see that difference between salient pole machine, cylindrical pole machine. I already explained in the synchronous machine. Please try to refer that. So there I told salient pole machine can be called as a low speed machine. Cylindrical pole machine can be called as high speed machine. Most of the synchronous motors are salient pole type. So it is applicable for, it is preferable for low speed applications. Therefore, synchronous motors prefer for low speed applications. So one more reason why synchronous motors are salient pole type means, most of the synchronous motors salient pole type means, salient pole synchronous motor are more stable due to some extra reluctance power. So this one also, please try to refer power angle curves. In power angle curves topic, I told generally if you take a cylindrical pole synchronous motor, you will be having only electromagnetic power is the output. Okay, because there in a cylindrical pole machine, air gap is uniform along D and Q axis. Therefore, I don't have any variable air gap concept. I don't have any variable reluctance principle. I won't be having any reluctance power in a cylindrical machine. But whereas a salient pole machine, because of the non-uniform air gap. Along D axis, air gap is minimum. Along Q axis, air gap is the maximum. Because of the variable air gap, because of the variable reluctance principle, reluctance for will come into picture. That extra reluctance for is the advantage. Because of this extra reluctance for, silent pole synchronous motor is more stable than cylindrical pole synchronous machine. That's why in most of the synchronous motors are against the silent pole synchronous motors. And see, since synchronous motor, the name itself indicates it is always running at n equal to ns. Synchronous motor always rotate only at a synchronous speed. Okay, because due to locking of stator poles and rotor poles. Stator poles will enter into locking with the rotor poles. So that's why it will be keeping on rotating with only one particular speed, nothing but synchronous speed. So synchronous motor always rotate at a synchronous speed due to magnetic locking with the stator poles and the rotor poles. And let me have some applications regarding synchronous motor. You can use synchronous motor for large power, low head pumps, reciprocating pumps, compressors, steel mills and rolling mills, induced draught fans, crushers and blowers. Okay, and last one is very important. Synchronous motor can be used as a synchronous condenser. This you might have known already. Synchronous condenser nothing but over excited synchronous motor used for power factor correction. Okay, nothing but synchronous motor can be used as a synchronous condenser. Synchronous condenser nothing but if you over excite the synchronous motor, that synchronous motor becomes synchronous condenser, which is used for power factor correction. Okay, so very important point. Synchronous, it is used as synchronous condenser for improving power factor. Okay, and see, I told you synchronous motor is not a self-starting motor because of inertia. The rotor cannot able to respond for the fast and continuous reversal of armature current. So please try to refer, once again I am saying, please try to refer simple loop diagram of synchronous motor. Then only it will be very easy for you to follow. Okay, since it is not a self-starting motor, your TST value is equal to starting torque equals to 0. TST by TFL value it becomes 0 here because 0 by TFL it becomes 0. TFL by TFL by 0, so nothing but infinite. So TST by TFL 0, TFL by TST infinite is the value for synchronous motor. Okay, and as I told you, these are the starting waves of synchronous motor. Before starting auxiliary motor starting, please try to note down all those things. Whatever I had given here, this portion, please try to note down. right? Now see, starting methods of synchronous motor. See, once again I'm just saying, please try to refer simple loop diagram of synchronous motor. There I had given reason why synchronous motor is not a self-starting motor. Okay. And see, this is actually because of inertia. I can say simple answer, because of inertia, the rotor cannot able to respond for the fast and continuous reversal of armature current. Though armature current is AC, it will rotor treat the current as DC because of inertia. Suppose if you overcome the inertia of that rotor, so obviously, so your synchronous motor will start. Let us see. So these are the starting methods of synchronous motor: auxiliary motor starting method, induction motor starting or damper winding starting, synchronous induction motor starting. In first one, auxiliary motor starting, so it's simple. It's nothing but synchronous motor having a rotor here. I just place field winding here. Okay, and we are placing armature winding on the stator. Just see, this is nothing but armature winding. Okay, and why I'm using here auto transformer or star delta starter means, you know, already it's common sense that in synchronous motor, V equals to, what is the formula? Supply voltage equals to back EMF plus IAZS. So during standstill condition, during starting condition, I can say that at a standstill condition, or I can say at a starting condition, your back EMF equal to, what is the value? 0. Therefore, V equal to 0 plus IAZS. IA equal to V by ZS. This value, numerator is no, generally V minus IA equals V minus E by ZS. That E value is 0 here. That's why your numerator value is more, so obvious IA is more. To limit this high starting currents, we are using starters. So nothing but auto transformer starter and a star delta starter. This regarding starters, we already explained in induction motor. Induction motor, starting methods of induction motor topic is there. There I told you auto transformer starter and star delta starter, all those things. So simply you are using here starter to reduce high starting currents. That's it. Okay. And C, to reduce high starting currents, we are using starter, auto transformer starter, or I can star delta starter. Now here my question here is, generally I told you, in a three-phase machine, what are the conditions for producing rotating magnetic field? Means you have to see two conditions. What are the two conditions? Windings, three-phase winding should be physically displaced by 120 degrees, and three-phase current should be time displaced 120 electrical. Okay. So these are the two conditions you have to satisfy for production of RMF. In case of synchronous motor, yes, if you see here R phase, Y phase, B phase windings, they are physically displaced by, 120 electrical. Okay. At the same time, you are taking three-phase supply from this R phase, Y phase. From, let me take this one as bus bar. Okay. It is taking supply from a bus bar. Here three-phase currents are time displaced by 120 electric. Like example, IA, IB, IR, IY, IB. IR equals to IM cos of omega IM cos omega t. IY equals IM cos of omega t minus 120. IB equals to IM cos of omega t plus 120, like that. Okay. So here currents are time displaced to 120. Windings are physically displaced to 120. Okay. So obviously, if you follow these two conditions, rotating magnetic field will produce. Okay. So let me show that the RMF which is produced in stator here. Let me show like this. See this one. I'm just erasing this one because generally this indication for making you understand that we are placing armature winding on the stator. Okay, just you understood? No, just let me erase this one. We are placing here armature windings, R phase, Y phase, B phase. Now, since windings are physically displaced 120 electrical and currents are time displaced 120 electrical, so obviously, yes, rotating magnetic field is produced. Let us see here poles formed on the stator surface. Example, magnetic field is produced on the stator and it is moving. RMF is what? Rotating magnetic field means what? Magnetic field is produced on the stator and it is moving. Example, it is moving with this magnetic field. So stator rotating magnetic field is rotating with speed, ns synchronous speed. That depends on your poles. Example, let me take synchronous motor poles. I'll take 20 poles. Okay, at that time, what is the synchronous speed here? 120 into frequency, let me take 50 Hz, 50 by poles 20. What about this value? So 300 RPM, 300 RPM. So whatever magnetic field produced on the stator surface of your synchronous motor, it rotates with the 300 RPM in this case, in this example, okay. Now let us see. So up to that, please try to understand. We are taking three-phase supply from bus bar. Three-phase currents are time displacement 120 electrical. Windings are physical displacement 120 electrical. Rotating magnetic field is produced. It is rotating with 300 RPM in this example. And here starters are used to reduce high starting currents. Okay. Now, please don't give DC supply to the field winding now only. Don't give DC supply to the field winding. Because our ultimate motto is here, we have to overcome the inertia of your we have to overcome the inertia of rotor of synchronous motor. You have to follow the steps. First one, just take connect supply, three-phase supply to synchronous motor. So on the stator surface, RMF is produced. It is rotating with the 300 RPM with number of poles of synchronous motor. If I take 20, okay. Now it is rotating. So RMF is rotating. Very good. Now please don't give DC supply now only to the field winding. Don't give. Okay, we have to first overcome the inertia of your rotor of your synchronous motor. For that, what we are doing here, we are using one small pony motor. So nothing more, I am just using one small pony motor. Pony motor, nothing but it's a small induction motor. I am just using one pony motor here, nothing but a small induction motor. You can use anyway. You can use not only pony motor, you can use DC motor also. Okay, depending on the supply available here. Suppose if it is single phase supply is available, so let me use on a single phase pony motor. Okay, single phase induction motor. Let me use here. Or if DC supply is available here, please use DC motor. It's your wish. Depending on the application, depending on the availability of a supply, you can use induction motor or DC motor, whatever. Okay. Yes, it is coupled. This rotor is mechanically coupled with this pony motor. After giving supply to armature winding which is placed in the stator, whenever RMF is produced, now by using this pony motor, okay, you are giving electrical supply to this induction motor, no? So mechanical power will be developed here. It is coupled with your rotor. So it will rotate rotor. Please rotate rotor of your synchronous motor by using induction motor at nearer to synchronous speed, at nearer to 300 RPM. To be frank, generally we will take pony motor poles. I'll take here poles of pony motor. Poles of pony motor will be equal to synchronous motor poles -2. I'll tell reason also why I have to take -2 only. -2. Synchronous motor poles, how much here I have taken here? 20. -2, how much? 18 poles. Now, if it is the synchronous, if induction motor poles are 18 in this example, what is the speed of this induction motor? N equals to 120 into F, 50 by poles 18. It will be around 333.33 RPM. So by using induction motor, we are rotating the rotor of synchronous motor at nearer to synchronous speed, nothing but nearer to 300 RPM. That too, I am rotating at somewhat nearer to 300 means what? 333 is nearer to 300, as well as 270 or 280 also nearer to 300 only. But try to see that speed of induction motor, pony motor, it should be above 300 and should be nearer to 300. So that means when it is possible, if we take poles -2 only, it is possible. So 333.33 RPM you are getting here. With this speed, rotate rotor of your synchronous motor. Whenever you are rotating rotor of synchronous motor, okay, so with this speed, so inertia will be overcome. Inertia of your synchronous motor rotor is overcome. Is it clear? Inertia overcome. Whenever inertia is overcome, then give DC supply to field winding. Whenever you are giving DC supply to field winding, Already rotor is rotating with what speed? 333.33 rpm. Inertia is overcome. Inertia is overcome. If we give DC supply now, yes, on the rotor poles will be formed. Example, let me take north pole, south pole, like the forms are formed. Poles are formed. Okay. Already rotor is rotating. Now you are giving DC supply to the field winding. So poles formed on the poles formed on the rotor. So already with 333.33 with that speed is rotating, rotor is rotating. So now poles formed. Now these poles are rotating, and already your on the side surface these poles are rotating. At one particular instant, rotor poles will enter into magnetic locking with stator poles. Whenever rotor poles come stator poles enter into locking, magnetic locking, from there onwards, it will be rotating with only synchronous speed. Will be rotating with only with the synchronous speed. Okay. And after, whenever they will enter into magnetic locking, if you disconnect your pony motor also, it will be keeping on running. Like this, we are starting the synchronous motor. Okay, is it clear? Please try to understand. Very simple. So first, just give 3-phase supply to whom your synchronous motor. So here, poles formed on the stator surface. They are rotating with 300 rpm for this example. For number of poles, if I take 20 for synchronous motor, it is rotating with 300 rpm. Don't give DC supply to field winding now only, because I need to overcome the inertia of your rotor of synchronous motor. So that can be possible by rotating rotor of synchronous motor by using a pony motor. With what speed? You have to run rotor of your synchronous motor at nearer to synchronous speed. That means pony motor poles you should take synchronous motor poles -2 you should take. 20 minus 2 you will get 18. Okay. 20 minus 2 you will get 18 here. 120 into 50 by 18 you will get 333.33. With that speed, your induction motor rotating your rotor. So obviously inertia is overcome. Okay, whenever inertia is overcome, you just give DC supply to the field winding. Now already rotor is rotating, inertia is overcome. Now the rotor poles are formed here depending on the DC supply. Okay, and rotor poles formed here. At one particular instant, rotor poles will enter into locking with stator poles. Okay, whenever they will enter into magnetic locking, if you disconnect your induction motor also, pony motor also, it will be keeping on rotating. Okay, now you may get one doubt. So why we have to take induction motor poles, pony motor poles -2 only? Why can't we take +2 here? Suppose if you take +2, I'm saying, if you take poles of pony motor is equals to synchronous motor poles, if you take +2 if you take, so at that it becomes 20 +2, you'll get how much? 22 poles you'll get. Here, at the time n equals to 120 into 50 by poles, if you can take 22 here, you'll get 272.72 rpm, something like that. Okay, 272.72 rpm. That means, yes, 272.72 also it is nearer to 300, whereas 333.33 is also nearer to 300. But why I am taking above 300 means, if I take the speed of induction motor above 300 rpm, so if you are rotating rotor with 333.33 rpm, from that speed slowly you have, from that 333.33 rpm, it slowly speed is reducing. It will come to 300. It will come to 300 rpm. At that time, I can say that rotor poles and stator poles will enter into locking. I told you. So from there onwards, synchronous motor will be keeping on rotating with 300 rpm only, 300 rpm only. That is smooth operation will be there. From 333.33 rpm, slowly it will come to 300 rpm. So in the meanwhile, rotor poles and stator poles will enter into locking. So they will be keeping on, from there onwards it will be keeping on running with synchronous speed only. Okay. Suppose if you take +2, your speed of your induction motor becomes how much? 272.72 rpm. Is it clear? So from this speed, if rotor poles has to enter into locking with stator poles, means from this 272.72, if it has to reach 300 rpm, so rotor has to jump from this 272.72 rpm to 300 rpm. You'll be having some jerk will be there. Jerk operation will be there. So operation will not smooth. Therefore, please don't take pony motor poles, synchronous motor poles +2. please take pony motor poles equals to synchronous motor poles minus 2, then only operation will be very smooth. I can write here pony motor poles of pony motor equals synchronous motor poles minus 2. Y means for smooth operation, for smooth operation, for smooth operation, from smooth operation, because from 333 RPM it will come to 300 RPM smoothly. Whereas if you take like this, okay, I mean corresponding to 22 poles, your speed of your induction motor is 272.72 RPM. From this 272.72, if it has to reach 300 RPM, some jerk operation will be there. I can write here, if you take like this, pony motor poles, synchronous motor poles plus 2, if you take operation not smooth, some jerk operation will be there. Jerk operation will come into picture. Jerk operation, because rotor has to jump from 272.72 RPM to 300 RPM. That's the reason you should take only pony motor poles, synchronous motor poles minus 2. Okay, is it clear? Yes. Next, here, what is the use of this resistance here? I just got some extra resistance here. It's very important examination point of view also. So many PhD they are asking this one. What is the use of this resistance value? See guys, starting I told you have to run rotor of your synchronous motor by using pony motor. Initially don't give DC supply told. Don't give DC supply. Suppose if rotor winding is, if I'm not giving DC supply to field winding. Suppose if I won't use this resistance, if I keep this field winding open like this, if I keep field winding open like this, open like this, what will happen in this case? Observe closely. What will happen if I keep open like this only? Initially I told we should not give DC supply to the field winding. Suppose if I leave this field winding open, what will happen? Suppose it is already RMF is produced here. By flux is produced, it is rotating with 300 RPM. If you rotate your induction motor, okay, this I mean if you rotate this induction motor with how much here? 333.33 RPM. Here 300 is the speed. Flux speed how much here? Flux, what is the speed of flux? E proportional to ns minus n relation is there, no? So let me discuss the EMF induced in field winding. I'm saying for field winding. So ns means speed of your flux. How much? 300 RPM. And if you run rotor with the induction motor with 333.33 RPM, so because of the relative speed, EMF will be induced across the field winding. In fact, guys, let me say clearly. In fact, during starting condition, what is the speed of your rotor? I can say 0. Yes or no? Already flux is rotating, no? Stator on the stator, armature flux is rotating with 300 RPM. This is the speed of your armature flux, which is based on the stator. If starting condition, if I take the speed of the rotor as 0, ns minus n, 300 minus 0. So relative speed is very large. Because of this large relative speed, large amount of EMF will be induced. Where? Across field winding. Large amount of EMF is induced across field winding. Because of that large induced EMF, what will happen to your field winding insulation? It will get damaged. So field winding insulation will get damaged because of this extra large amount of EMF induced across your field winding during starting condition. So to avoid this, what you have to do? Please, during starting condition, let me use let me correct some extra resistance value. Let me short circuit field winding. Please short circuit field winding. Field winding should be short circuited by using a resistance like this. Okay, by the resistance like this. Okay, during starting condition. So what will happen because of that? Some EMF will be dropped, some voltage will drop across this resistance. So large amount of EMF will not induce across field winding. So because of this extra resistance value, some EMF will be, you will be having some drop across your resistance. So less amount of EMF will be induced across field winding, so that the field winding insulation will not be damaged. Very simple thing. During starting condition, if field winding, we are not giving DC supply to the field winding. If you want short circuit field winding with this resistor, if you open that field winding, so here speed of magnetic field is 300 RPM. During starting condition, speed of rotor is 0. Because of the relative speed, large amount of EMF will be induced across field winding. So because of that, field winding insulation will get damaged, which is not desirable. So during starting condition, field winding should be short circuited by using resistance. So because of that, some resistance will drop, some voltage drop across, some voltage drop will come across your resistance. So small amount of EMF will be induced across field winding. So because of that, insulation will not damage for field winding. Okay. So this point is important. Remaining notes you can see by explanation you can understand clearly. So this REX point is important here. What is the use of this resistance here? I can write here. During starting condition, field winding should not be open. Field winding should not be open. Comma. Field winding should be short circuited. With I can say extra resistance. With extra resistance. Field winding should be short circuited with extra resistance so that field winding insulation will not damage. Because some voltage drop will come across your this resistance, so that field winding insulation will not damage. Is it clear? That's the reason why during starting condition this acceleration should be short circuit. Field winding should be short circuited with this resistance. Okay. And one more advantage is that because of this acceleration value. What is that? This resistance provide closed path for the flow of currents, for the flow of field currents. Because of that field flux will come into picture. Field flux. So because of the field flux, you'll get some torque. That torque helps synchronous motor in overcoming the inertia. So obviously, if you overcome, ultimately our main focus is we have to overcome the inertia of your synchronous motor. So this extra resistance, if I short circuit field winding with this resistance value, some current will flow, some flux will come into picture. Because of that flux, some torque will come into picture. That torque will overcome the inertia of your synchronous motor. That torque also helps in overcoming the inertia of rotor of synchronous motor. These are the two functions of this resistance value. Okay. So this is the function of this is the starting method of your synchronous motor. The two accelerated motor starting. We are using accelerated motor means we are using temporary motor, nothing but pony motor here. So same explanation will be there in damper winding and synchronous induction motor starting also. Ultimately, we have to overcome the inertia. That's it. How we are overcoming inertia? That is the case. Suppose in this method we are overcoming inertia of a rotor of synchronous motor by rotating a rotor with a small pony motor at nearer to synchronous speed. That's it. If whenever our inertia is overcome, now we are giving DC supply to the field winding. So that already for in the stator, armature flux is produced, nothing but rotating magnetic field is produced. And if you give DC supply to the field winding and the rotor, so on the rotor also field poles will be formed. At one particular instant, this rotor poles will enter into locking with the stator poles. From there onwards, the synchronous motor will be rotating with the synchronous speed 300 RPM, I can say. If you disconnect your accelerated motor from afterwards, it will be keeping on running. There is no need to connect induction motor after that. Okay, we can disconnect. And why we are short circuiting field winding with resistance value means simple. I told you during starting condition, N value if I take 0. So if I take speed of your rotating magnetic field Ns, because of the relative speed, large amount of EMF will be induced across this field winding. So because of that field winding, insulation will get damaged. So to avoid insulation, to avoid damaging of field insulation, field winding should be short circuited by using resistance like this. So because of field winding short circuited by using a resistance, some drop occurs across this field winding, so that some less amount of EMF will be induced across field winding, so that insulation will not damage. And one more function, because of this resistance value, it provides path for your field current. Because of that, field flux will come into picture. Because of that, torque will come into picture. It helps the synchronous motor rotor in overcoming the inertia. And see, one problem in this method cannot use. Auxiliary motor starting method cannot use if synchronous motor is under load condition. Whenever synchronous motor is under no load condition only, we can use this method. Why means, If it is under load condition, so inertia will be very much. So because already load is connected. So synchronous motor rotor is having inertia. So you have to overcome a large amount of inertia. For that, rating of your induction motor, rating of your pony motor, rating of your auxiliary motor required is more. You get my question? Suppose if I use this method, if a synchronous motor is under load condition, we have to, inertia at that case will be very large because rotor is having already inertia. If you connect some load, so because of that load also you will be having some inertia. You have to overcome large amount of inertia. So obviously requirement of your auxiliary motor rating will be more. Okay, that's why this method is used only when synchronous motor is under no load condition. There should not be any load. Simply I have to overcome the inertia of this rotor. So requirement of your rating of your auxiliary motor also less. Rating of auxiliary motor is less than the rating of synchronous motor. Suppose if it is under load condition, rating required will be very large. Okay, therefore just remember, auxiliary motor starting method used only if synchronous motor is under no load condition, not under loaded condition. Because under load condition, requirement of auxiliary motor rating is more. Is it clear? Right. Next, let me go for damper winding starting method. This is also very simple. We already discussed in silent pole machine, we will place damper winding. We will place damper winding in the slots which are made under pole shoe. In this pole shoe, you have to provide some slots. In the slots, we have to place this damper winding. Is it clear? So here one thing here understood. Just already we discussed about damper winding in different silent pole machine. Anyway, let us see. During starting condition, everybody. During starting condition, what is the speed of your synchronous motor? 0. What is the speed of, do you have any EMF into the damper winding? Yes. Y means ED proportional to NS minus N. NS means what? Whenever you are giving 3-phase supply to synchronous motor, as I told you, 3-phase comes at time displacement 120 electrical and windings are placed here physically 120 electrical maintenance we maintained here. So automatically RMF will be produced. So let me show whatever I just showed south pole, north pole here. So similarly here also south pole, north pole, it will be forward, it will be rotating. It will be rotating. So speed of this RMF is nothing but NS. During starting condition, rotor speed is how much here? 0. So obviously because of the relative speed, EMF will be induced in a damper winding. So because of this damper winding EMF, damping current will come into picture. Because of this damping current, damping flux will come into picture. Because of this damping flux, interaction between this armature flux, whatever produced on the stator, interaction between armature flux and the damper winding flux gives you damping torque. Is it clear? This damping torque will overcome the inertia of synchronous motor rotor. And it will overcome the inertia, it will rotate. So whenever N increases, whenever N reaches NS, whenever rotor speed reaches NS value, it checks here once again, NS minus NS, damping EMF 0, damping current 0, damping flux 0, damping torque becomes 0. Whenever synchronous motor reaches synchronous speed, then damper winding action will not be there. Only during starting condition, it will overcome the inertia, it will bring rotor speed from 0 to NS. Whenever N equal to NS is coming, so I can say that damping action will be absent. Okay. And what about this RX? As usual, see guys, whatever I had given expressed here, same thing here also. Initially, don't give DC supply to the field winding, because if I give DC, if I give DC supply to the field winding, we should not give DC supply to the field winding. We should not give DC supply to the field winding. At the same time, we should not keep field winding open also. Why should not open field winding here? I told you. Here, RMF is produced. It links with your field winding. Large amount of EMF will be induced. There will be chance of damaging our field insulation. To avoid that, what you have to do? So to avoid it, what you have to do? You have to short circuit field winding with this resistor. Whatever I told here, same explanation here. Because this resistor, it will avoid damaging of field insulation. At the same time, it provides path for field current, field flux. Some torque will come into picture. This torque help damping torque in overcome the inertia of your synchronous motor rotor. Okay, and as I told you, first of all, don't give D supply because damping torque has to come. Damping torque has to come here. Okay, damping torque has to come. So this because of the damping torque, it will rotate rotor. Okay, whenever inertia is overcome, then give D supply to the field winding. Then poles will be formed on the rotor. At one particular instant, rotor poles and stator poles will enter into locking. From there onwards, it will be keeping on running with synchronous speed. Whenever it is running with synchronous speed, in damper winding, no EMF because NS minus NS, damping EMF 0, damping current 0, damping flux 0, damping torque becomes 0. Same thing. Whatever had given expressed here, same expressed there also. That's why I spend more time here. So same explanation here. When you have to give DC supply, why you have to field winding, why you have to short circuit field winding, whatever explained there, same expressed here also. Okay. And last one, synchronous induction motor starting. Synchronous induction motor starting. Here, observe guys clearly. Yeah. Synchronous induction motor starting. Very simple. We discussed already in induction machine chapter. We discussed a slip ring induction motor. In a slip ring induction motor, during starting, we are connecting some extra resistance value. Why? Because TST proportional to R2 plus REX would release, you might have known in the induction machine. Please try to recollect that. Whenever if I add some extra resistance value to the already existing rotor resistance R2, starting torque will increase. That starting torque, so starting torque will be more in slip ring induction motor because of this extra resistance value connected in series with R2. Here also, in synchronous induction motor starting, we are giving three-phase supply. Three-phase supply is giving here. Rotor of synchronous induction motor starting is similar to rotor of a slip ring induction motor. Okay, so this is about R2 value, this is about R2 value, R2 value, R2 value, and this is about REX value, REX, REX, REX. So during starting condition, we are adding extra resistance value to this R2, to this R2, to this R2. See, REX is added to this R2, REX is added to this R2, REX is added to this R2. Very simple. Now, this is very, whenever REX is added to the R2, so what will happen to TST value? Increase. Whenever TST increases, so obvious inertia is overcome. Inertia is overcome. Inertia is overcome. Inertia is overcome. During, whenever inertia is overcome and running and slowly this extra resistance should be cut down. And running condition, REX should not be there. It should be cut down because loss will increases. So already explained in slip ring induction motor. Okay. So on running condition, this REX has to be cut down. Okay. Slowly, whenever inertia is overcome, so this REX has to be cut down, and you have to give D supply to the field windings. This you can take entire this windings as two terminals. You can take this as two terminals at last by having this arrangement. Okay. If I give D supply to the field winding, when after inertia is overcome, now on the rotor, as usual, poles will be formed. So inertia is overcome. At one particular instant, this rotor poles will enter into locking with stator poles. It will be keeping on running with what? It will be keeping on running with what? Synchronous speed. Synchronous speed. Okay. Simple. So you have to, it's a simple point here. In synchronous induction motor starting, okay. Yeah. Synchronous induction motor. Actually, synchronous induction motor starting, if I use synchronous induction motor starting for a synchronous motor, that motor can be called as synduction motor. I can write here synduction motor, synduction motor, synduction motor, synduction motor. Synduction motor rotor is similar to slip ring induction motor rotor. So where TST proportional to R2 plus REX, R2 plus REX. So I am just connecting this extra resistance value to this R2. So TST increases, it will overcome the inertia. Now whenever inertia is overcome, just give this supply to your field winding. So poles will be formed. So whenever these rotor poles and stator poles will enter into locking at one particular instant, whenever they will enter into locking, from there onwards, that motor will be running with synchronous speed. Okay. Here in this if I use synchronous induction motor, a synchronous induction motor, so this motor can be called a induction motor. Okay, this rotor is similar to slip ring induction motor. Okay, nothing but it will be a star connection. Please try to refer once slip ring induction motor so that it will be easy for you. Okay, please note down all those things.